Welcome to the video for Lecture 12, Section 4 for BBE 4023 Process Control and Instrumentation. This video describes how to create unique input or forcing functions. We have used step, impulse, sinusoidal, and ramp functions as input functions in earlier sections. They all have Laplace transforms in the Laplace transformation table, and they all started or made their change beginning at time t equals 0. Sometimes people want to use other functions as input functions, or they want to have changes begin at other times rather than time t equals 0. So the goal of this section is to create unique input functions using step, impulse, and ramp function elements. Notation is important to be able to communicate the functions. We will use the term u of t to represent a unit step change. We will use delta of t to represent unit impulse functions. And we will use a times t of t to represent ramp functions, where a is the ramp slope. This slide shows two step functions. They are similar but not identical. The top figure shows the standard positive step function of magnitude a at time t equals 0. Off to the left are the equations that say that at time t less than t equals 0, the value of the function is 0. At time t greater than 0, the value of the function is equal to a. The lower figure shows a positive step change of magnitude a at time t equals t1. The step change for the lower figure has a delay. For this figure, the value of f of t is equal to 0 for time t less than t1. For time t greater than t1, the value of the function is equal to a. We need a way to write the expression describing this kind of delay. Here is example 13-1 from the course packet. We have a positive pulse. The value of the function f for time t is less than 0 is 0. Then from time t equals 0 to time t equals h, the value of the function is a. Then at time t greater than h, the value of the function is equal to 0 again. The first step is to draw the function. The second step is to write the expression for each change. For the step up change, we write a times u of t. Remember that u of t is the expression for a unit step change. The value plus a gives the direction, positive in this case, and the magnitude a. The next change is at time t equals h. We have a step down. We write minus a times u of t minus h. The t minus h tells us when the step down occurs. By combining the equations, we write f of t equals a times u of t minus u of t minus h, as shown in the bottom of the slide. This expression is our time domain expression that describes the pulse that starts at time t equals 0 and ends at time t equals h. Our next task is to transform the input function in the time domain to the input function in the Laplace domain. We do that by taking the Laplace transformation. We do each term separately. The first term, a times u of t, is transformed using equations 6 and 3 of the Laplace transformation table. The result is a over s. The second term is transformed using the translation of function rule on page 5-3 of the course packet and equations 6 and 3 of the Laplace transformation table. When we use the translation of function, we get a over s times e to the minus hs. This can be reorganized as shown on the slide. This is the Laplace domain expression for the time domain expression at the top of this slide that describes the positive pulse of magnitude a shown on the previous slide. Here is example 13-2. We are given a diagram. This diagram has three step changes. The first step change is a plus a step change at time t equals 0. The second step change is a minus 2 times a step change at time t equals t1. The third step change is a change of plus a at time t equals t2. The time domain expression is shown here. The first term on the right side of the equal sign is the first step change of magnitude a at time t equals 0. In some respects, we could write the time as t minus 0, but that is not common practice. The second term describes the negative step change at time t equals t1. The magnitude and direction are given by the minus 2 times a. The t minus t1 indicates the time of the change. The third step change is written as a times u of t minus t2. The Laplace is taken by using the terms in the Laplace transformation table and the translation of function rule. The result is the equation at the bottom of the page. Example 13-3 is shown here. Again, we are given a figure to describe the input function. Our task is to write the time domain expression f of t and to take the Laplace transformation to find f of s. If we look at this figure, we can see that we have two changes. One change is the ramp that starts at time t equals 0. The second change is the ramp stopping at time t equals 1. So our time domain expression will have two terms. We can see that the ramp slope is a because the value after one time unit is a. We should also note that the ramp begins at time t equals 0. So the first term of our time domain expression is a times t of t. The next change begins at time t equals 1. The ramp stops. Now this seems to be a tricky concept for many students. To stop a ramp, we need to subtract the initial ramp. That is done by writing minus a times t of t minus 1. The minus 1 is because the initial ramp stops at time t equals 1. The next step is to take the Laplace transformations. The first term is transformed using equation 8 of the Laplace transformation table. The second term is transformed using equation 8 and the translation of function rule. The resulting Laplace domain expression is shown here in the lower right corner of the slide. Ramps seem to cause students a lot of difficulty. It may be because with ramps the term a times t of t keeps trying to ramp up. Students forget that they have to add a term to make the ramp stop rising. And if we want to make the ramp go downward at a negative a slope beginning at time t equals 1, we need to subtract a second negative ramp amount to make the line slope downward. Here is example 13-4. This is the figure and equation for an impulse of magnitude a at time t equals 0. Using the terminology that we introduced in this section, the input functions we write f of t equals a times delta of t. The Laplace transformation, using equation 4 of the Laplace transformation table, is f of s equals a. If we want to input the impulse at another time, we need to write the time domain function differently and use the translation of function rule. Here is an impulse of magnitude a that is imposed at time t equals 2. When we have a delay of 2 units of time like this, the time term in the function changes to t minus 2. The inverse is a times e to the minus 2 times s after using equation 4 and the translation of function rule. This brings me to the end of the Lecture 12 Section 4 video on input functions. Write down any questions you have and bring them up in class.